So, in this lecture I will discuss, as I said in the last lecture, I will discuss determinant functions. So, as we saw last time that when V is a k vector space, of dimension n, then the alternating multilinear maps ALT IV, alternating multilinear forms. So, I do not write that k in the notation. This is the set of all alternating I multilinear forms. This is interesting. This is a k vector space, and I am going to discuss only the case when cardinality of I is also n, which is the dimension. Because we have seen in the last lecture that when cardinality of I is more than the dimension, then 0 is the only alternating multilinear map on V. So, therefore, they are 0 vector spaces. So, we do not need to study them. This is the first interesting case when cardinality I equal to the dimension, and in this case I will prove that this is one dimensional vector space. We will prove that dimension of this vector space, dimension k. Now, I will write, instead of I will keep writing NV. This is 1. So, this is what I am preparing today for. In any case, elements of this vector space alt NV are called determinant functions on V. So, they are multilinear, alternating multilinear n forms. I will now keep using the n forms on V, and they have the properties of the determinants, as we will see. So, the first easy lemma that I have already done it earlier, but I want to do it again more. So, let Vi I in I be a family of vectors in V, and I have given for any j in j, a j in I, let us write xj to be the combination of these Vi's, ai, j, Vi, and let us let F be an alternating multilinear form. So, and we take cardinality I equal to dimension V. Then, if I evaluate F on this tuple xj, I want to know what do we get. So, this is equal to F of, let us write this I is, for a simplicity, I will write the set I equal to n star n, which is 1 to n, and this x1 is a combination j equal to 1. So, it is a combination, and in this sum I is varying. So, I will call it I1 in a I. So, it is A I1 1 V I1. Similarly, x2, which is I2 in I, A I2 2 V I2, and so on. In in I, A in N V in. And now we use the fact that F is multilinear. So, what will happen is all these AIs will come out. So, this sum will run over all the tuples I1 to In in I power n, AI1 1 AIN n and f of VI1 VIN. This is very, very simple so far. This we have seen so far. But in this now, who will survive? Because if 2 in this sum is running over all the tuples in I power n, but some of the tuples may have some 2 different coordinates may be equal, and in that case then f of this will be 0. So, that will not contribute anything. So, this sum is equal to sum I1 to In in I power n, and not only that, with all distinct coordinates. Then this is AI1 1 AIN n times f of VI1 VIN. So, repeated coordinate tuples we have removed, but then remember this you can think of a tuple where all coordinates are distinct, then the cardinality of the set of these coordinates, this cardinality will be n, which is cardinality I. That means you can think this as a permutation of 1 to n. So, that is this tuple I1 to In will correspond to a permutation, to the permutation sigma, where sigma is defined like this: image of 1 is I1, image of 2 is I2, image of n is In. This is a permutation on I. So, this sum is nothing but a summation. Now, I write, instead of the tuple big notation, I will write sigma in SI, and then this is a product. Product is running over J from 1 to n, A sigma J J. This is this one times f of V sigma 1 V sigma 2 V sigma n. But we have seen that whenever you have a multilinear map F, and when you permit the coordinate, and if it is alternating, then the sign will come out. So, this is same as sine of sigma times f of V1 to Vn. So, that gives us, that tells us that this this coefficient, which is for the if you call this matrix A to be Aij, then the summation running over permutations of I sin sigma times this product j in I A sigma j j. I should write bracket here. This is important. This is the coefficient of that f of this times f of v1 to vn. This was the value of that tuple f of xj. So this one could define this one as a determinant of the matrix A. It is so important because of this formula. Okay. So before I go on to the formal properties of this, I want to state the main theorem of determinant theory. So main theorem of determinant theory. So in the above observation, if you would take V1 to Vn as a basis of V, that means then any alternating multilinear form on V, this form is uniquely determined by its values on the tuple, basis tuple, because any other tuple you write in terms of the basis V1 to Vn as xj equal to aij vi summation, and then you have to know the value of this is determinant A times this value. So it is uniquely determined by basis value of an alternating form on a basis vector. So let us start with the basis. So let V equal to V1 to Vn be a k basis of V, then there exists a unique determinant function I will denote it by this will depend on the basis V. So delta V is the determinant function, means it is an element in alt NV such that delta V evaluated at this basis vector V1 to Vn is 1. Unique is very important. So moreover, actually we can write down what is delta V. Moreover, for any other x tuple, x is x1 to xn in V power n, write each xj is summation aij vi. This we can do it because I is from 1 to n, because V1 to Vn is a basis, and if I take any such arbitrary tuple, then delta V evaluated at x1 to xn is equal to summation is in sigma sin sigma product is running over j 1 to n a sigma of j comma j. This delta V evaluated at V1 to Vn. but this is we are demanding 1. So, it is this quantity, and this constant, this is a constant, it is a linear form. So, the values are constants, values are scalars. So, this linear form has a importance, and this one I will call, this is the determinant of the coefficient matrix. The determinant of A will be then called this quantity, sigma in SI sin sigma, product j is from 1 to n, A sigma j j, which is a scalar. It is called the determinant of the coefficient matrix. A equal to AJ. This is a matrix in MNK. And by the way, so this it is also immediate that when I in this sum is running over all permutations. So, when I replace sigma by sigma inverse in this, then the sign of sigma, this is because sign of sigma and sign of sigma inverse are same. That is immediately from the cycle decomposition, canonical cycle decomposition of sigma. The number of cycles are same, disjoint cycles are same. The only thing they are written in a reverse direction, and sign does not change. And then this product changes, I is from 1 to n, AI sigma I. So, this is in fact the determinant of the transpose matrix. So, actually immediately we will get from here that determinant of A equal to determinant of the transpose matrix. So, that is immediate from the definition. So, we only have to prove the existence of delta V and uniqueness of delta V. So, uniqueness is clear because on any tuple this value is 1. So, it is uniquely determined by this formula in fact, because this is 1. Okay. So, proof of the theorem, though existence of delta V. This should be an alternating map from V power n to k with delta V on V1 to Vn is 1. So, in particular delta V is never 0, it is non-zero, not never 0, it is non-zero alternating multilinear form. Okay. So, this also we have already constructed. So, the only thing we have given is a basis, V1 to Vn is a basis, k basis of V, and that look at the dual basis, that is V1 star, Vn star, they are linear forms on V, linear forms, and they form V star, which is V1 star. This is a basis of the dual space, is a k basis of the dual space of V, V star of V. And remember, they are defined, their defining equations are V star I evaluated at Vj, this is precisely delta Hij, this is Kronecker delta, Kronecker symbol. That means V star evaluated at Vi is 1 and V star evaluated at any other basis element is 0. And last time I also told you a recipe, if you have given so many linear maps, then we can construct a multilinear map, that is a product map. So, the product map F equal to product I in I is from 1 to n Vi star. Think of this is a map from V power n to k defined by any x1 to xn. This is mapped to product I is from 1 to n Vi star evaluated at xi. This makes sense, and this is clearly n multilinear. Because VI's are linear and the product, so it's because of the distributive and so on. And once I have a linear, I have a multilinear map, then we know how to make it alternating. Last lecture, we have this recipe AF. AF is by definition summation sigma in SI sin sigma and then sigma f. This is a map from V power n to k. All these sigma f's are multilinear. So, this sum is multilinear. So, AF is definitely multilinear, and we proved AF is actually alternating n multilinear form. Form is because the values are in k. And this is what I want to check. I want to take delta V by definition this. Because it is alternating and multilinear, it definitely belongs to alt NV. And all that we want to show that now is delta V enough, therefore only to show that delta V evaluated at V1 to Vn is 1. But well, that you evaluate delta V, let us evaluate. Actually we know how to evaluate delta V. Let us evaluate not only at this tuple but any arbitrary tuple. So, delta V evaluated at x1 to xn, where x1 to xn is arbitrary tuple V power n, and because each xj we can write in terms of the basis Aij Vi, I is from 1 to n. This by the above, because it is alternating and so on, this we know the formula. This is summation running over sigma permutations sin sigma product j equal to 1 to n a sigma j times what? Actually this is I directly wrote it. This is, and then this thing evaluated delta V evaluated at V1 to Vn. So, and actually you could have written one more step in between here. See, if I had to, I want to write one more step here. I write this came out of the fact that they are Vi star evaluated at x sigma I, because that is what the definition of this is. First you permute the tuple and then apply this, and so this comes out this. So, and then this will go or disappear. So, we get this formula. In particular, when you put x1 equal to V1, xn equal to V1, we will get delta V evaluated at V1 to Vn equal to 1. Because in that case these Aij's are diagonal 1 1 1 1 1, and so this sum will be actually 1, because they will only be the once on the diagonal and everywhere else it is 0. So, it is only one. Only one term will survive in this sum, namely sigma is equal to identity. All other terms will vanish. Okay. So, that proves this is the required determinant function that we were looking for, that on delta V on V1 to Vn is 1, and so that is what I will prove now, to prove that it is one dimensional. Okay. So, let us write one corollary to this. Let take V to be a basis, V1 to Vn, basis of V, and delta V be the corresponding alternating form with unique delta V evaluated on V1 to Vn is 1. Then for every f in alt n V and every tuple x1 to xn in V power n, we can write down the value of f on this tuple, and that is nothing but delta V evaluated on x1 to xn f of V1 to Vn. That simply means, so that is this is a constant. So, every multilinear form f is uniquely determined by its value on a basis. So that means we can give a map, let us give a map from alt n V to k, any alternating form maps to this V1 to Vn. This is an isomorphism, the k linear isomorphism. In particular, it is one dimensional. In particular, dimension of the alternating forms is 1, and once the dimension is 1, we know delta V, this form is non-zero. So, this must be a basis, and delta V is a basis of alt n V. And this formula is just proved the same way. You write x1 to xn in terms of combination of each xj, you write as aij vi, j is from 1 to n, and apply the earlier process, and this is what we have defined. This is nothing but this is nothing but the sum, this quantity we have known, this is the sum over sigma in Si, sin sigma, product j is from 1 to n, a sigma j comma j. This is just the generalized distributivity formula, and that shows everything. So we will continue after the break.